All right, welcome to class. First of all, I know we have our exam on Thursday, so how this class is going to work today, I asked you to watch a video. We're going to take some time to make sure you understand the concepts in those videos before we move on. We might get to a little bit of new content, but content that will not be tested on in this exam. And then the last at least half hour of class is going to be unstructured review time. You can stay, you can leave, you can ask me questions, you can hang out and hear other people's questions. However you want to use that time. I do have on the chalkboard, and feel free to go over it any time, write down what your study methods are, because it will probably be helpful for everybody in the class. Right? I have some study methods that I know of, but what works for me might not work for you. What works for you might work for another student. Share those study methods at some point. Let's see. I handed back content check number 2 to most of you. We'll get around to the rest of you here in a bit. I graded the part 1 on Moodle. There is one question, order the molecules in order of permeability. Something went wrong, I think, in the Moodle settings, right? So when I set it up, it actually graded it backwards than how it should have graded. So then I did a regrade, and once I did a regrade, I got a few emails saying, this isn't at all what I put on, something happened, my answers got all shuffled, something happened, all right? What I'm gonna do is go back in and figure out how to give you just all that point, all right? Because something went wrong. If you got it correct, great, awesome. If you didn't, you're gonna get that point back. I think it's like half a point, actually. All right. I had a lot of questions come in over the weekend. I do not have time in class to answer all of the questions that came in through that anonymous question asker, but I have answered them all through links and videos and worksheets on this slide. If it was your question or this question you are reading now and you're like, oh yeah, I want to know that too. Click on the link, right, and hopefully this will explain it a little bit better. I tried to find videos and links that I hadn't previously linked as a resource to try to give you something new. If you downloaded this PowerPoint before like 7:30 this morning, you probably don't have these slides, but I have added them to the student slides, so you will have access to these. All right, so I'm glad questions are coming in. That means we were reviewing, we were studying for the exam. When I looked over the content check, right, there are some common questions that came up, and so I wanted to post some resources for those common questions as well, right? One of which is like polymers and monomers, just trying to remember what goes to what, right? I have provided you with a video. I've made a study sheet that kind of summarizes everything. And then if you're somebody who likes to listen to songs, I found a polymer song that maybe, I mean, it's a little nerdy, but maybe it'll get stuck in your head and you'll remember it. All right, same with organelles and functions, just having trouble remembering it. I also found another song, Organelles Have Jobs. That one was kind of catchy. That one got stuck in my head a little bit. As well as another song and then a website comparing an organelle, all the organelles, to parts of a city.
I actually made a Dungeons and Dragons map at one point based on the insides of a cell.
Yeah, oh, that's very cool. Yeah, I love those creative uses. So find ways that work to help you remember them. Protein structure, that was another big one. I linked Eva Sister's video to help you understand protein structure a little bit better, that primary, secondary, tertiary, quaternary. I can review this in our review time later this class period if we're still kind of stuck on that. All right, I think that's all the announcements I had to say. I want us to start off class with a review of that video. I want you to make sure you understand what I was talking about in that video that I posted that you were supposed to look at before class. And if you didn't, you're going to be kind of lost, right? That's why you make sure you need to watch these videos before you come to class. The video was talking about the types of transport. Right? I elaborated a little bit more on facilitated diffusion, particularly the different types of transmembrane proteins that can be used and how they function. And then we talked about active transport, which was both primary active transport and secondary active transport. Right? Big thing with active transport, it needs energy because now solutes are moving against their gradient. They are no longer going from high to low, they're going from low to high, which solutes just do not do naturally. So to review all of this information, I have some questions for us, and I actually have an activity. I'm going to pass out some molecules and an answer sheet to every third person here. And I want you to work with those around you to figure out your molecule, what type of transport is it going to utilize, right? Facilitated diffusion, simple diffusion, or active transport. I want you to put it on what you think is the correct answer, and then once you have decided that those are the answers you're going to go with, right? You can flip over those sheets and the answers are provided so you can check your answers. We're actually going to do this a few times, so for the first timer here I have about 3 minutes just so we can all kind of get situated. And then I think we're going to swap molecules a couple of times. Give everybody lots of practice. So let's see, I have a sheet here. I'm going to start with 2 because I know we have a bigger class. Let's see. Some here. Hopefully here. Molecules. Molecules. You want to work as a group of 4? Yeah. All right. Perfect. Let's see. Lucy, can I have you work with the 2 people immediately behind you here? And then Jonathan, I'll have you work those behind you here. We'll do a group of 4. That's perfect because I have one last group. It's going good. Early start. Hello. Yes. I gave you 2. I'm going to do another one.
I believe these are the answers.
We have such a variety of that. Do you? It's not too bad, actually, yeah. They all use the same type of transport though, don't they? Yep. Yep. Yeah. Yes. All right, give me just a minute to say. Wait, is that true? I checked number one. What else?
That one's the one.
Yeah. I will make sure to fix it. I'll forget if you don't hang on. How's it going here? That's true. Yeah, it's moving against its gradient. Polarity charges always going to be active. Yep.
Oh, yeah.
Is it going here? Oh, you got one of each, huh? Did we check? Large molecule. I was moving with, so probably facilitated. Oh. Right there. Yep. Yep. So you can check your answers. They look right. Non-polar with fusion. Yeah. So getting to be a larger molecule, but it's not large enough yet. Imagine simple. All right, that was 3 minutes. I'm gonna have you move your molecules to the next group. So all those little black cards, let's pass it. Which way? Yes, that would be to the right. No, to the left.
To the left.
Pass it to the left, to the group on the left. And
Where are we gonna?
whose group has not exchanged yet?
What we gave on?
Did you exchange your molecules with someone? I gave them away. Okay. Where have all my molecules gone? Make sure we're passing along. I have 2 groups with no molecules. Find another group that has excess molecules. I will take up a passenger.
I might ask.
Alrighty, there we go.
That's actually so
Yes, use the molecules, answer those questions about the molecules. You might not need them, they'll just be prompted. Yes.
That's one that needs energy, right?
Yeah. Oh, that's okay. Okay, good. Any questions? Yep, that's what we did. Alrighty. Ready to do this activity one more time? Yeah. Nope, you were correct. All right, pass those molecules to a new group if you haven't already. We'll do another 2 minutes and then we will move on. I think we're passing like towards the middle. I'll take your last group. So it looks like we're looking for some. How do you know that?
Oh, yeah.
Do I have a group that does not have a new set of molecules? I will bring them towards you. Cell number 8. Yeah, it's not one or the other, but the outside is water body.
Oh yeah, that's right.
Yes, yes. All right. Questions? All right. Last year I did this as a game. A little bit more chaotic. Yeah, I like this too.
If it's going against it, that's for sure. Otherwise, you're looking for it's like
Yeah. Still active. Yep. If it's against its gradient, it doesn't matter what it is. It has to be active because cells are just not. They don't want to naturally move against its gradient. Yep. Yeah. Unless it's an ion. Yep. All right. Any questions I can clarify on this practice few rounds here?
What does it mean for a molecule to move against or with its gradient?
Yeah, so it's moving with its gradient. It's going to move how solutes naturally want to move, which is from areas of high to areas to low. If it's against its gradient, we're going from areas that are already low to areas that are high, which solutes are not going to do naturally. That's why we have to use energy to get them to move. Yeah, good question. Anything else? All right, I will come around and collect everything. I will leave them up front here, so if you did want to practice, say, during our study part of our lecture today, you are free to take some molecules and practice. I have another review for you, all right, because I also talked about osmosis in the video. I want you to take a few minutes and answer these 2 questions. Some cards. Injected solution that proves that Any questions here?
That's what I figured.
Yeah, not for like these introductory level classes.
Let us know
If you ever have to the closed-toe shoes, those are a must. That's,
Yes.
even though it's not dangerous chemicals. Yes.
Takes you too much to handle.
High tension means like it's harder.
Questions on osmosis? Ah, there's a trouble.
I'm doing worse and worse. It's like better and better. Oh, I'm actually but the first week I was like up at 5 o'clock ready to go. And now I'm like
What does hypertonic mean when it comes Yes. So hyper means excess. An analogy means like hyper is like yeah. So it's gonna have excess of solute from that side here into another side. Yeah. There you go. I'm actually gonna switch back to here. Grab my last
Because that would imply that the drug did that on purpose, and that would be illegal.
That's a fair point. All right. Group number one here, we have this doctor who thought he injected a patient with an isotonic solution. But the patient died, right? So that was a pretty big mistake. Autopsy revealed that the red blood cells had burst. Was that solution actually isotonic? No. What was likely that solution? Yeah, likely hypotonic, right? So the solution that was being injected had more solutes around it, right? Then there were solutes in the red blood cells, right? The water, had fewer solutes. I even messed that up just by trying to explain it, right? Had fewer solutes in that solution than the red blood cell had. So the red blood cell had more solutes. Water is going to rush in. That red blood cell is going to swell to the point where it's going to burst, right? Now, Miles was telling me the tutors last night gave them a really good example of how to remember this. Hyper sounds like hippo. Hippos are large, right? So hypo contains larger amounts of solutes, right? It's those kind of like study methods that really help sometimes. All right, and then I have that true or false on the bottom. Osmosis only moves via simple diffusion. True or false?
False.
False. Osmosis can move via simple diffusion, but it can also move via facilitated diffusion using those transport proteins called aquaporins, right? So I should really reword that question to say water only moves via simple diffusion, because osmosis implies simple diffusion. Yeah, I think I worded that a little tricky. This would be an example of, if I worded it like that, and I realized after the fact that, oh, that caused confusion, I would likely give you that point back on the exam. Yes, so that, great teaching moment here. All right, any other questions about osmosis or water movement? About the lecture that I had you watch over the weekend?
why would an excess of water on the outside cause its cell to burst?
Excess of water on the outside? Well, if that excess of water has fewer solutes. It all depends on the solute solution that's in the water, right? So if there are fewer solutes in that excess water, right, the water is going to move in towards where there are more solutes, try to maintain equilibrium.
Actually, like for uniport, symport, and antiport,
Mm-hmm.
for like if they can go like either way, in or out, depending on the concentration.
Yeah, so we were talking
Not
about
just one way, like it can go both ways.
if it can go both ways with like a symport or an antiporter.
Or if it only goes from like outside the cell to inside the cell. Or like
I believe it's only one way, right? So if we say need a solute on the inside of the cell, a uniporter, which is a transport protein, is only going to transport one type of solute, one direction. I do not believe it can change direction if it needs to be transported the other way. I think in that case you might have to have like the protein oriented different. That would be my hypothesis. Yeah. Because
This would also be the reason why we can't make like a one size fits all vaccine, right? Because there'd be too many different chemical compounds.
it could be. I think we're getting more into like the biology of an individual at that point too. Yeah. Yeah, antiporters then are always going to move two solutes opposite directions, and then a symport is always going to move two solutes in one direction.
So the hypertonic would cause the water to leave the cell?
Yeah, if the solution was hypertonic instead of hypotonic in this example, we would see water leaving the cell in excess, and then likely the patient would also pass, but probably due to cells being shriveled up, right? Too much water leaving the red blood cells. Yeah. Any other question?
so going back to
Mhm.
going back to the antiport, for this like do they go at the same time? Or is it one goes and then the other goes?
Ooh. I know there's an answer. I'm trying to remember off the top of my head. I think it's one binds, it changes conformation, lets the other go. The next solute comes in, binds, changes conformation, lets it go on the other side. I believe it's one at a time.
Right, and like when it goes in, is it because of like, or is it going from high to low and then the other one's going from low to high?
Nope, they're both going from high to low.
Okay.
Yeah, yep. Anything else? Because I had you watch it outside of class. I really want to make sure we understand it. All right. Then we're going to introduce some new information here, simply because we don't have enough class periods in a semester to not do so. But this information will be tested on exam 2. So we're going to talk about reactions and enzymes. All right, so energy and chemical reactions. So if we're talking about chemical reactions, we have to talk about energy. And energy is defined as the ability to promote change or to do work, right? To make something happen. Likely you've heard of these two types of energy before, right? We can have kinetic energy, which is associated with movement. Or we could have potential energy, which is like stored energy or energy that has the potential to exist, right? I think about a good analogy for this is somebody shooting a bow and arrow, right? The arrow, when it's been released, is moving through the air. It contains energy. That is kinetic energy. When you draw a bow back and the arrow is in place, but you haven't released it yet, all right, that bow is under tension, right? So as soon as you release it, movement's going to happen, right? But when it's held in place, It's potential energy, right?
This is
It's
how our
there,
muscles
it's
work.
ready.
This is how our muscles work,
How muscles work.
because it's constantly pulling on something.
Yes and no. I think muscle working is a lot more complicated, but you could think of it that way, right? If you're tensing up, right, you're kind of holding your muscles in place, and then when you release it, right, maybe the energy is dissipated, it's being used. You could maybe make that analogy. All right, oftentimes when we're talking about chemical reactions, though, we're talking about chemical energy, right, which is different than just say plain kinetic energy or plain potential energy. Kinetic energy is the energy that is held within a bond, right, the energy in a molecular bond. It's a form of potential energy. All right, so bonds, they have energy, right? They have energy that is ready to be released, right, as soon as that bond breaks. So the bond is a potential energy. The bond breaking and releasing the energy would be kinetic energy. All right, so in biology, we talk about a lot of different forms of energy, right? It can come from multiple different sources. We can have chemical energy, energy in bonds, and that's really what we will focus on. But we can have energy from light, right? So sunlight, or heat, right? Other types of kinetic energy, maybe in like muscle movement, right? Electrical energy, we're using energy in ionic gradients, right? There's a wide variety which the body can obtain energy from. We're going to focus on this chemical energy, so the energy specifically held within the bonds. All right, in order to talk about energy, we have to talk just a little bit of physics, right? Physics is not my strong suit, so I have made it as simple as possible here. We're going to talk about the first two laws of thermodynamics. Right? You might have heard about these before. The first law is the conservation of energy, meaning energy cannot be created and it cannot be destroyed. It's simply changing form. Right? So energy isn't going to be spontaneously created out of nothing. Right? It's also not going to be completely destroyed and go away. It's just going to change where that energy is located. So if we're thinking chemical energy, all right, maybe you are eating an ice cream cone. Right? That ice cream cone contains a lot of sugar molecules. As your body processes those sugar molecules, it's breaking down the bonds. Right? By breaking down the bonds, we're converting that chemical energy into kinetic energy, energy we can use to, say, ride our bikes or run around, right? That sugar rush that we get. Right? So that's a good example of how chemical energy can change forms. Light energy, right? The energy we get from sunlight can change forms, and a really good example of this is photosynthesis, which we'll talk about next unit. Or after the exam, I should say. So light energy, right? Plants harvest the energy in the light, right? Harvest like the photons. And when they harvest that energy, they are going through photosynthesis. They are generating chemical energy in the form of glucose, right? So photosynthesis makes glucose. Right? So energy can be converted from a variety of different forms. It's not going to be created out of nowhere. It's not going to completely go away and be destroyed.
Technically, all four pictures are connected to each other. Because glucose is sugar and sugar is in ice cream.
Yeah, exactly. Maybe the sugar in your ice cream came from a plant derivative. Yeah, like cane sugar. All right, our second law of thermodynamics, right, is that when we transfer energy from one form to another, we're actually going to increase in entropy. All right, so entropy is defined as the degree of disorder. I like this image because I think it kind of gets this concept across, right? If we're highly ordered, right, and we increase in entropy, right, all those pieces get more disordered because there is more entropy, more disorder into the equation. Right, and as we introduce more entropy, more disorder, that means there's less energy available for organisms to actually harness and do work. Oh, I thought I had another image on there. I think it's on my next slide. All right, so entropy is disorder. As we get more disordered, there is less energy for organisms to use. Let's do a quick break. All right. I have pictures of two different images here, and I want you to answer those questions.
Yeah, because it's transferring.
You just gave it to me, yes. Yeah. Your other one though. What was that? Yours is online. Okay. All right, what do we think? Which one has more entropy?
The one that's dissolved.
Yeah, the one that's dissolved, right? There's more disorder, more chaos. It's not this nice lattice structure of sodium and chlorides anymore, right? That are all ionically bonded together, right? But rather they're being dissolved. There's more disorder in the picture here. All right, a few more slides here. So we have to think about entropy. We also have to think about enthalpy, and I always struggle over that word. I think it's the N next to the TH, which is total energy. We also have to think about free energy, which is actually the energy that the cell can use, right? So enthalpy is a total amount of energy. It's both entropy, which is unusable energy, because there's more disorder into the equation, as well as the free energy, energy that we can actually use, energy that cells can harness. Right, so energy transformations like I mentioned, typically increase in entropy, disorder that cannot be harnessed for work. But there's also this free energy in the equation, right? The free energy is the availability to actually do the work, and we call this Gibbs free energy.
This is also called G-force, right?
Called
Wait,
what?
That's something else.
G-force? Maybe it's G. I often abbreviate it as G, and you will see this G come up quite a few times. Yeah, so the G is correct, right? So when we want to figure out is a equation or is a molecular reaction going to happen on its own, or do we have to expend energy for that equation to work, right? We are going to look at the amount of free energy available, the amount that is available to do the work. All right, so let's take a look at how we would use this Gibbs free energy, right? So is a reaction spontaneous? Is the reaction just going to happen on its own? Or does the reaction need energy, need an input, right? An energy that happens, or excuse me, a reaction that happens on its own is an exothermic reaction, right? And we would say that the reaction is spontaneous, so it's exergonic, right? EX being on both of those terms there. But you'll notice that the change in Gibbs free energy here, this delta G, is going to be less than 0. That is the key, right? If I tell you any equation has a delta G less than 0, maybe I say it's negative 0.5, right? That's automatically going to cue you in to that this is an exothermic reaction. This reaction will happen on its own. It will happen spontaneously. Right? But what happens though is that the products produced will end up having less energy, right, than the reactants. So if we look at an image here, we have our two reactants, which are these two yellow dots. The Gibbs free energy is less than 0, so this reaction is a go-ahead, right? It's going to give out some energy, but the products are going to have lesser amounts of energy than it started with in the reactants, right? We're losing a little bit of energy. Right, opposite to an exothermic reaction is an endothermic reaction. This is a reaction that will not happen on its own. We need an input of energy in order for this to happen. So that delta G, that change in Gibbs free energy, is going to be greater than 0. Right, so it's not going to happen on its own. It's not spontaneous. We would say it's endergonic. However, if we look at what happens to the energy during this reaction, we see that energy is inputted into the equation, right, as well as the reactants, and the result is that our products are going to have a higher amount of energy than what the reactants started out with. Right, so exactly opposite of our spontaneous reaction. All right, you know I like analogies, so I like to talk about this analogy in terms of your dorm room, all right? It is really easy to just toss your clothes and papers on your desk and make a mess in your dorm room, right? It's really easy for your dorm to get messy, right? That'll just happen spontaneously. But to clean it up requires an input of energy on your part, right? That's not going to happen spontaneously. That's not as easy to do. You have to exert energy in order to make that room clean again. All right, so that's like our exergonic versus our endergonic reactions here. All right, this is where our molecule of ATP comes into play. All right, if we look at ATP, right, adenine triphosphate here, it has these 3 phosphate groups, right? And an ATP, it's an energy currency, and it's an energy currency because these phosphate groups, the bonds that hold them together, contain large amounts of energy, right? So to break off a phosphate group, is going to provide energy for reactions to occur. And in fact, when this bond breaks, right, when this reaction happens, we have a delta G of negative 7.3, right? That's less than 0. So we know this is going to happen spontaneously. All right, so that energy has now been freed up, and that energy can be used by the cell to fuel the other reactions it might have to do. Maybe that's active transport, right? We need energy to move that gradient, to move the solute against its gradient, right? That energy is coming from the breaking off of this phosphate group because our delta G is a negative, right? So it happens spontaneously. We can give off energy. All right, this is great. Let's put this in an example to really understand it.
So I think I remember, but where do the hydrogen molecules come from in the second picture? Is that from the water molecule?
Hydrogen molecules, oh, on either end here?
Yeah.
Yes, because it's a hydrolysis reaction. Yep, a hydrolysis uses the water, right? So the water is providing those hydrogens to either side here. Yes, that's a great point. All right.
Thank you, Dad.
So cells are using ATP because it's an exergonic reaction to break off that phosphate group. And they use it in the endergonic reactions, the reactions that do not happen by themselves that need an input of energy. ATP being that input of energy here, right? So we can couple different types of reactions together. So we're going to couple an endergonic reaction to an exergonic reaction, right? So say we want to take glucose and phosphate and make glucose 6-phosphate plus a water molecule. This reaction on its own has a delta G of 3.3. That's above 0. That means it's endergonic, which means it's not going to happen on its own. It's not going to happen spontaneously. It needs an input of energy. All right, well, we know ATP, if we were to take off a phosphate group, like in the second reaction, we get a delta G of negative 7.3. Right, so if we combine these two reactions together, right, we couple them together, so basically we're adding both of these values together, we get a reaction that in total has a delta G of negative 0.4. All right, we've coupled this endergonic reaction with a reaction that's exergonic to make the reaction as a whole exergonic and spontaneous, right? But we needed to couple it with that energy source in order for it to happen. All right, I think this is my last slide before I'm going to start us on a review here. So when we think about reactions, right, there are a couple of ways reactions can be affected, how fast they occur. Temperature and concentration being two of these ways, right? So for most reactions to proceed, we have to break some chemical bonds. Others have to form, right? We're rearranging our molecules, we're rearranging our atoms, right? So our substances kind of have to collide with one another in order for those reactions to occur, right? So if we had ATP way over on the far side, right, and our glucose phosphate that we had in our last example on the opposite end of the cell, they're not going to interact, right? So that reaction's not going to go just because they're not near each other. Now, when you put cells in higher temperatures, right, and I give you a very extreme example of opposite ends of the cell, but maybe they're in the same area, just not immediately colliding in with one another. But if we were to warm up the temperature, that makes our molecules move faster, right? If molecules are moving faster, they're moving more, they should collide more often. And therefore, the reactions should happen a bit more quickly. The same is true with the concentrations of our reactions. Right, if we have a lot of ATP and a lot of glucose phosphate, right, it's likely they're going to collide with each other more often than if those reactions were very sparse. Right, they might be moving around, but they're not colliding with each other as often. right? So temperature and concentration really makes a difference as to how fast a reaction can occur.
So that would imply like that powdered sugar would dissolve faster than grain sugar would in a glass of water?
Oh, theoretically, yeah. Yeah. I don't know if that's actually the case. I don't know the chemical compositions there, but theoretically, yeah, that's the right concept.
Usually you make powder. Well, usually you can get something like a drink mix. It's usually made into a fine powder.
Yeah, yep. That way it dissolves a little bit easier and faster. Yep. All right. I'm actually going to leave us on this slide because I think this will be a great slide to come back to when we are done with our exam. I want to use the rest of the time for you to study. All right, like I said, you can